Hello. In this video, we will introduce the SNR after the MIMO equalization. We will focus on the linear MIMO equalizer. We will discuss two equalizers. One is zero forcing. This is one zero forcing equalizer. The other one is the MMSE equalizer. Both are linear MIMO equalizer. MMSE means minimal mean square error. So it is a little bit difficult to get the formula for MMSE equalizer's SNR. It is a little bit easier for zero forcing equalizer. So this series video will focus on MMSE, but at first I will introduce zero forcing equalizer's SNR calculation. So now let us look at the MIMO system model. This model is like this one. This N is the noise vector, and this X is the sending signal, the original signal. So the H is the channel coefficients matrix. So Y is the received signal vector. So Y is a vector, H is a matrix, X is a vector, N is a vector. So now we will assume the noise is a Gaussian random signal. So MIMO linear equalization is to find a matrix G. Okay, use the G, we try to recover the original signal X. So we call the recovered signal as hat X. Okay, so this hat X, this is G. This is we call it the equalizer matrix. So for the zero forcing equalizer, we know the equalization matrix G is this one, So this H means the conjugate symmetric transpose, conjugate transpose. So this is the equalizer matrix G. So we get the estimate signal X is X hat is GY. We know the Y is HX plus N. So now we know the G matrix like this one. So we use this H, reverse H, and HX plus N. So now we multiply with each one, So we get H, reverse and HX plus H, reverse HN. So now this two one can cancel each other. This is reverse. This is the original matrix. So the both are cancelled. So finally we get the expression is X plus H, reverse and HN. So now we know the estimated signal is like this one. So in this one, we can see the X hat like this one, such as X1, X2, X3. There are three elements. So it's equal to maybe X1, X2, X3, and plus this. We call this is height n. Height n is this one. So each element is here. So we call such as n1 height, n2 height, n3 height. So now the signal power is 1. We assume the original signal is power is 1. So now we need to calculate each element's power. It means this is the noise power after equalizing. So now we need to calculate each element's power, but it's a little bit difficult to write math equation. So we use the covariance matrix. So this is a vector. So we use the vector times the vectors conjugate transpose. So now we get a matrix. This is a covariance matrix. So this one is n1 height, n1. Oh, here has a conjugate, n1 height, n2 conjugate, n1 height, n3 conjugate. So the second row is n2 times n1 conjugate, n2 height, n2 conjugate, n2 height, n3 conjugate. So this one is n3 n1 conjugate, n3 n2 conjugate, n3 n3 conjugate. Okay, so we want to use this one, this covariance matrix. So now we do this one, similar like this one. Okay, now we let us try to write the math equation. So this is the covariance matrix, but we are interested in the diagonal elements. So we only interested in the such as the element on L's row and L's column. It means we only care about the elements in the diagonal lines. So we use this expression. So we use the LL means the elements on L's row and L's column. So we use this one and use this one to substitute this one. So we get this one, and this conjugate is this conjugate, and transpose, conjugate and transpose. So now this one, the last one, we can get this one. So it's easy to see, because this signal is a random variable. So we need to use we need to find the expectation. So we use the expectation, but the h, I mean the channel coefficients, are determined. So it is not a random variable. So the random variable only is the noise. So the expectation computation is on the noise. So we use this one to here, only on the noise. So this one is this one. We know the Gaussian random variable is we assume they are independent and zero mean. So this one we will get we assume the noise power is sigma square. So we get the sigma square is a diagonal matrix. So we use this one, sigma square times I. I means identical matrix, means 1 1 1 1 1, the other is 0. So now we eliminated the noise, but we get the noise part here. So this is the final expression. So we cancelled this one, this two one can be cancelled. So we finally get this one. So this is the noise. This is the noise power. So we assume the signal power is 1. So the SNR is 1 over sigma. I mean this one. Get the elements on the else row and else column. So this is the SNR. So one I want to say is that the zero forcing equalizer has no interference between the signals. It means this one x1, x2, x3 is equal to x1, x2, x3 and plus some noise. So each one only has his original signal, no other signal interference. So we call, in this scenario, I mean the zero forcing equalizer, the SINR is equal to SNR, so we call it SNR. So the SNR is this one, the final is this one. Let us analyze this one. We get some intuition. So we do some eigenvalue decomposition. Because this matrix is a conjugate transpose symmetric matrix. It means this conjugate transpose is equal to itself. So this type matrix, we do the decomposition, we can get this one. We know that for a general matrix such as A, we do the eigenvalue decomposition, we should get Q times sigma and times Q inverse. So because this type matrix, so this one we can use conjugate transpose. It means Q inverse is equal to Q transpose conjugate. So let's do some we get this, we want to get this one's inverse. So now we want to get this one's inverse. So this one's inverse is like this one, because it is Q sigma Q H inverse. So we need to do this inverse for here, but we know this Q H is a Q inverse. So inverse is itself. So it's Q here, Q. This one is go to here, so it's Q H. So this sigma we need to get the inverse, because sigma is a diagonal matrix. So this minus one, this inverse, it means each element we get the 1 over this one, 1 over each element, 1 over each element. So it is this one. So now we can write, because we want to get this matrix L, the one element on the diagonal. So we know such as there is 4 matrix A, B, C, D, A times B times C times D. We want to get this the results, the element on the mth row and nth column. So we can treat these two as a one matrix such as is E. So we know E and D, we get Mn. So we know two matrix multiplication. We want to get one element on the result. So we need to use the E's mth row and times the matrix D's nth column. This is nth column, this mth row on the matrix E. So we know this it is equal to D nth column and E n mth row times this is a vector, this is a row vector, this is a vector. So the result is a number, maybe a complex number. So this one we can say it is D nth row, nth column. So we want to get the ABC's mth row. So we know if two matrix multiplication such as AB, we want to get the m row. So we use A's mth row times B's each column. So we can write this one is A's nth row and use the whole B and C times C. So for this one, we want to get the L. So we need to use this one's QH L's column and the Q's L's row. So we assume the QH is equal to Q1, Q2, blah blah blah, QL. Each Q1, QL is a column vector. So the Q's mth row is equal to QL conjugate and transpose. So this one we get the QL conjugate transpose. For this one we get QL. So finally we get this one. So here I need to modify. This one is sigma, this is lambda. We use a different, so I need to change it. So here is sigma. Anyway, here QL is a row vector and this is a column vector and times a diagonal matrix. So each one is this one times this one and times this one is one element, and plus this one times this one times this one, the second. So plus all, we get this one. We get this one. Here we should get a square, because this one times this one, we get a square. Now this lambda I is the ith element on the matrix lambda's diagonal, on the diagonal. So this is so the finally SINR for zero forcing, we get this one. Here we also get the square. So now let us look at detailed. The detailed. If the H, and H. This matrix decomposition, eigenvalue decomposition, contains some very small eigenvalue. That means such at least one, even only one lambda I is very small, such as the 0.9, 0.8, there are one very small, such as this one, 0.0001. So this inverse, the lambda, this one is very big. It's 10,000. It's very big. So if even there are only one very small eigenvalue, so we will cause the final SNR will very small for all the streams, for all the signal, for each signal recover, we get a very low SNR. So this is the very, very small eigenvalues effect on the zero forcing equalizer. So we will got a not very good result after the zero forcing equalizer if there are very small eigenvalue. So okay, now we have discussed the zero forcing equalizers SNR formula. So next video we will become to discuss the MMSE's SNR formula. There are two formulas. They are basically the same. That means use different form, but they are the same. We will next video we will introduce these two formulas. We will introduce how to get these two formulas. They are the same. Maybe sometimes we can use this one, sometimes we can use this one. It's a little bit too difficult to get the two formulas from the beginning. I mean, from the at very beginning, we get the noise, get the interference, and then we try to calculate the SNR for MMSE. Okay, let's let's discuss it on next video. Okay, thank you everyone. Bye.